Good morning, class. I will be discussing today chapter 9, which is electric circuits. And the focus of our discussion is more on problem solving. So we will be solving problems using Ohm's law for a simple series circuit. We will be relating resistance and resistivity, solve problems including electric power, solve circuit problems that include internal resistance of batteries, and then we will be solving complex circuit problems by applying Kirchhoff's rule. And then finally, we will be analyzing resistor circuits with series connection and parallel connection. So electric current is the amount of charge per unit time that passes through a surface that is perpendicular to the motion of the charge. So the formula is simply current is equal to the change in charge divided by the change in time. So simply we can write value for current as I is equal to Q divided by time. In this formula, so we can derive the formula for charge. So charge is simply equal to I multiplied by time. And then for time, of course, that is equal to charge divided by the current. Again, in this equation, so charge is expressed in coulomb, and then time is of course expressed in second. So coulomb per second, so this is equal to ampere. So the unit for current is ampere. In this problem about a pocket calculator, so we have in this problem we have the given potential difference. So the potential difference here is 3.0 volts battery. Okay guys, please be reminded that in solving problems we need to identify the units, and then based on the units we can already determine the quantity. For example, if the given unit is volts, so meaning that is a potential difference or voltage. If the given is in terms of ampere, so that is the current. If the unit is expressed in ohms, that is resistance. Watts is for power, or simply watt, in which watt can be converted to kilowatts and horsepower. And then we also have the different values of resistivity and other quantities. So later you will be encountering different quantities, but the basic is the coulomb, the ampere, we have voltage and resistance. Again, in this problem, so we have the given current, which is 0.17 milliampere. So this is the value of the current, in which milliampere is expressed, of course, in milliampere. And then in terms of this problem, so we need to convert milliampere into ampere to make this system in one system, which is MKS system. So if the given unit is in volts, the other unit should be in ampere and resistance. So we are asked here the charge, okay, the amount of charge that flows in the circuit, and then the letter B is how much energy does the battery deliver to the calculator circuit. So in this formula again, or in this equation, so we have the given potential difference, so that is 3.0 battery or volts battery, and then we have the given current na 0.17 milliampere. So for us to get the value of the current, of course, we have this formula. So charge divided by time, or the change in charge over the change in time. So for us to get the value of charge, this is the formula, of course. Change in charge is equal to I multiplied by the change in time. In the problem, the charge is already given, so that's 17 milliampere, or that is expressed to 0.17 multiplied by 10 times to the negative 3 ampere. So this is the conversion from milliampere to ampere. And then also in the problem, the time is given, in which according to the problem in 1 hour, so meaning in 1 hour that is equivalent to 3,600 seconds. So just multiply the current with the time. So that's 0.17 times 10 to the negative 3 ampere multiplied by 3,600 seconds, so that is equal to 0.61 coulomb. Okay, so that's the value of charge, and that is the answer for letter A. For letter B, so we are asked to get the energy delivered to the calculator circuit. So we have this formula, which is energy is equal to charge times energy divided by charge. As you can notice, guys, okay, so the 3 volt here is the potential difference, and then this one is the value of the charge. If you can still remember, in our chapter 2 of our discussion, okay, we have the value of work, in which if we want to get the value of work, so that is simply F multiplied by X. And also, in that formula, or in that chapter, we can also get the power. So power is equal to work divided by time. in which work can be expressed in joule, and then time is in second. So we have joule per second, so that's equal to watts. Okay, and then also in the previous chapter, so we computed for the value of the potential difference, in which the value or the equation for potential difference is equal to work divided by the charge or the test charge. So we're going to use this formula for us to get the value of energy, in which the work here can be also expressed in energy, because in our previous chapters, so work is equal to the change in potential energy, and that is also equal to the change in kinetic energy. So we can conclude that work is also equal to an energy. So in that formula, we can use this one for us to solve for the value of the energy. So based on this, energy is equal to the potential difference multiplied by the charge. So we're going to use that formula to solve letter B. So energy is equal to the value of charge, which is 0.61 coulombs. So that's the computed value of charge on letter A. And then the value of the potential difference is 3.0 volts. So this is given in the problem. So 0.61 coulomb multiplied by 3 volts, so that is equal to 1.8 joule. How many electrons flow through a battery that delivers a current of 4.0 amperes for 15 seconds? So in this problem, we have the given current. So current is 4.0 ampere. Time is also given, 15 seconds. And then we are asked to get the number of electrons. In the previous chapter, we discussed how to get or to compute for the number of particle or the number of electrons, in which, if you still remember, so we have this formula. The number of electron is equal to the charge divided by the charge of electron. So we will be using this formula to compute for the number of electrons in this problem, but we need to get first the value of charge. So we can get the value of charge by using this formula for the current. So charge is equal again to current multiplied by time. So we just need to multiply 4 by 15 seconds. So we have 4.0 ampere multiplied by 15 seconds. So 4.0 ampere multiplied by 15 seconds, this is equivalent to 60 coulomb. After computing for the value of charge, we're going to use this value and substitute that to get the value of the number of electrons. So number of electrons is 60 coulomb divided by the charge of electron. So the charge of electron is equal to 1.6 negative times 10 to the negative 19 coulomb. So the charge of electron is negative 1.6 times 10 to the negative 19 coulomb, but we don't need to include the negative sign here because we are just referring to the magnitude. Okay, so the sign only shows that that is a negatively charged particle. So 60 coulomb divided by 1.6 times 10 to the negative 19 coulomb. So this is equal to 3.75 times 10 to the 20 power, okay, or 3.75 times 10 to the 20 electrons. So the number of electrons flowing through a battery that delivers a current of 4.0 amperes for 15 seconds is equal to 3.75 times 10 to the 20 electrons. So this is a slide about Ohm's law. So according to Ohm's law, so the resistance is equal to potential difference or voltage divided by the current. Again, the resistance here is expressed in R. Potential difference or voltage is in V, capital V. And then for current, we have I. Again, the formula for, or the Ohm's law states that resistance is directly proportional to the potential difference or voltage and inversely proportional to the current. So meaning, as the resistance increases, the voltage also increases. And then as the resistance increases, the current will be decreased. So that's the relation between the two. The same thing with the voltage. So voltage is directly proportional to the current. So R is expressed in ohms. This is the unit for resistance. I again is ampere. And then for the voltage or potential difference, this is expressed in volts. The filament in the light bulb in the resistor in the form of a thin piece of wire. So we have this given. Okay, according to the problem, we have two 1.5 volts battery. We have two 1.5 volts battery. So meaning we have the given voltage. So that is 2 times 1.5 volts. So 2 times 1.5 volts, that is equal to 3 volts. And then also given in the problem is the value of the current. So current is equal to 0.40 ampere. So we have 0.40 ampere in the denominator. So we are asked to get a resistance. So resistance is simply voltage divided by current. So voltage again is equal to 3.0 volts. So that is twice of the 1.5 volt battery. And then current is 0.40 ampere. So 3 divided by 0.40 ampere, the value of the resistance is 7.5 ohms. So this is another example or problem about Ohm's law. In this problem, we have 4.0 ampere. That is the value of the current. And then with a total resistance of 1000 ohms, resistance is 1000 ohms. So the question is, what net charge passes through any point in the circuit during a 30-second interval? Time is also given in this problem. That's 30 seconds. So we are asked to get the net charge, the value of Q, or change in Q, or the sum or the net charge, or sum of the charges. So here again, the formula for charge, or simply Q, that is equal to current multiplied by the change in time, or I multiplied by time. So we have the given current here, so that's equal to 4.0 ampere. And then we also have the given time, 30 seconds, so therefore we can already compute here the value of charge. So the value of charge here is equal to 4.0 ampere multiplied by 30 seconds. So this is equal to 120 coulomb. So this is the net charge. So if you are wondering why we did not use 1000 ohms in the equation, so as you can see, in the equation, the change in charge is just equal to current multiplied by the change in time. So in the equation, there's no presence, or resistance is not present in the equation. So therefore, we can neglect the given resistance, because we can still compute the value of charge even without using the resistance. When a light bulb is connected to a 3.5 battery, so we have the potential difference or voltage, so that's 3.5 volts. And then a current of 0.15 ampere. Current is given, 0.15 ampere. So we are asked to get a resistance. So again, resistance is simply V over I. V is 3.5 volts. Current is 0.15 ampere. So resistance here is equal to 23.33 ohms. An electric heater uses 6 ampere. 6 ampere is current. And then we have 120 volts. Again, we have the given voltage. And we are asked again to get the resistance. Again, this is the formula. So we have 120 volts divided by 6 ampere. So this is equal to 20 ohms. So the resistance here is equal to 20 ohms. A light bulb has a resistance of 520 ohms. Resistance is given, 520 ohms. How much current? We're looking for current when it is connected across 220 volts. Voltage is given, 220 volts. So let's derive the formula for current. Okay, again, the formula for resistance is V over I. So therefore, for us to get the voltage, so that's IR. And then for current, that is V over R. So we're going to use the formula V over R to compute for current. So V over R, voltage is 220 volts. Resistance, 520 ohms. So current is equal to 220 volts divided by 520 ohms. This is equal to 0.42 ampere. Another problem about Ohm's law, we are asked to get the potential drop. and that is equal to the potential difference, or V, or voltage. 7 ampere is the current. Then we have resistance, 36 ohms. So V is equal to IR. So this is equal to 7.0 ampere. The value of current, 36 ohms. Resistance, so 7.0 ampere multiplied by 36 ohms. This is equal to 252 volts. Okay, so we are done with Ohm's law, but the Ohm's law can be also applied in the different topics here. Okay, this one is resistance. Okay, this resistance is the resistance in a conductor or in a wire. So if we are discussing about a copper wire or a lead or a silver wire, so that's the conductor. Usually that is used in the wiring, or connecting one device to the circuit, or to the electric circuit. Okay, here again, R here is the resistance in the conductor or in the wire, and then we have here rho, or like that is also the unit we use, or the symbol we use for density. But in this case, this is not density, but this is the resistivity. So the unit is ohm meter. The L here is the length of the wire. So if this is the wire again, if this is the wire, so the length is this one. And then resistivity is whatever be the material. So the resistivity depends on the kind of material, if that is a silver, aluminum, copper, etc. The area here is the area of the copper wire, and area is equal to pi r squared. So this is the formula. So for us to get the area, we need to identify the diameter or radius. So given the radius, we can use pi r squared to compute per area. Or if the diameter is given, we can use pi d squared over 4. So this is the formula to get the area. So therefore, R can be also written as resistivity multiplied by length over pi r squared. And then in this formula, we can also derive the formula for length. So length is equal to cross multiply R multiplied by A divided by the resistivity. And then for area, of course, we can also derive for area. So area is simply resistivity multiplied by length divided by the resistance. So area is equal to resistivity multiplied by length, and then that is to be divided by again. So the area is equal to resistivity. So this is the resistivity. So here is the resistance. So we have, this should be density, or resistivity, I mean. Okay, here's the resistivity. So resistivity times length of the wire divided by the resistance. Okay, so let's proceed with the problem solving. Table, okay, as you can see here, for copper, that is equal to 1.72 times 10 to the negative 8. So that is the value of the resistivity of the copper wire. Again, resistivity is equal to 1.72 times 10 to the negative 8 ohm meter. So here is the value. The length of the wire is given also 35 meters. So we have here 35 meters. And then the area of the 35 meter 20 gauge copper wire is equal to 5.2 times 10 to the negative 7 ohm meter. So we have this value. So multiply the divide by 5.2 times 10 to the negative 7. So the answer for letter A is 1.2 ohms. The same process with letter B. The difference between letter A and letter B is of course the given. For letter B, the given length is 75 meters. And then the area given is 13 times 10 to the negative 7 square meter. Again, just compute that. Then the value is 0.99 ohm meter. So for letter A and letter B, they are using the same kind of wire. They are using the same copper wire. So the resistivity of copper wire or copper is 1.72 times 10 to the negative 8 ohm meter. Determine the length of the copper wire. We are looking for the value of length. We have the given resistance. resistance of the copper wire is 0.372 ohms, and then the cross-sectional area is equal to 6.35 times 10 to the negative 5 square meter. Of course, resistivity is given. Resistivity is 1.72 times 10 to the negative 8. So this is the resistivity for copper. Okay, so to compute for that, so length is equal to, according to our derivation, length is equal to R, resistance, multiplied by area, divided by the resistivity. Let's just substitute the given. Resistance is 0.372 ohms, area 6.35 times 10 to the negative 5 square meter, divided by the value of resistivity, 1.72 times 10 to the negative 8 ohm meter. So this is equal to 1373.37 meter. So the length of the copper wire is 1373.37 meters. The resistivity of the silver wire with radius is 4.5 times 10 to the negative 4 meter. So here's the radius of the wire. Again, if this is the wire, okay, the radius is, here's the radius, and radius is equal to 4.50 times 10 to the negative 4 meter. And then according to the problem, resistance is equal to, okay, we're looking for the resistance. So resistance is unknown. Okay, so that's the question in the problem. We have length of the wire, 4.00 meter. And then we have here 1.59 times 10 to the negative 8 ohm meter. So this is the value of the resistivity. 1.59 times 10 to the negative 8 ohm meter. So if you're going to verify if for silver wire, that is really 1.59 times 10 to the negative 8 ohm meter. So we can check again that in the table for resistivity. Okay, again, so we have the value of small r, which is the radius. L is 4 meters. Resistivity is 1.59 times 10 to the negative 8 ohm meter. So the question here is, find the value of resistance, and then resistance, again, the formula is rho L over area. So this is equal to rho, which is 1.59 times 10 to the negative 8 ohm meter. Okay, and then that is to be multiplied by length. So length is 4.00 meter, or 4 meters, divided by the area. How to compute for area? The area is, again, pi r squared. So pi multiplied by 4.5 times 10 to the negative 4 meter square. Okay, so this is the equation or the solution. So just multiply 1.59 times 10 to the negative 8 ohm meter multiplied by 4 divided by pi multiplied by 4.5 times 10 to the negative 4 meter square. So the value is 0.099 something, or this is equal to 0.10 ohms. So the resistance is 0.10 ohms. So this is the relation between the temperature coefficient of resistivity, or this value. Okay, so that is in relation to the resistivity and also to the, of course, to the temperature. So meaning what will happen to the resistance of the resistor if there is changes in the temperature. So if you still remember, in our linear expansion of metal, we have this formula for the linear expansion of metal. So LO 1 plus alpha, and then multiplied by T minus T naught. Okay, so this problem is about the linear expansion of metal, in which the alpha here is called the coefficient of linear expansion. But in our case here, the alpha here is called the temperature coefficient of resistivity, and that is constant. Okay, so for us to get the final resistance, so this is the final resistance, this is the initial resistance of the wire or of the conductor, And of course, we have the final temperature and initial temperature of the conductor or of the wire. So we have this problem. Okay, we have 4.45 ohms. R is equal to, so that's equal to RO, 4.45 ohms. And then temperature, initial temperature is 0 degree Celsius. So what is the resistance at 60 degree? So the final temperature is 60 degrees Celsius. And then we have the temperature coefficient, which is alpha. We have 4.3 times 10 to the negative 3 per Celsius degree. Okay, so that's the given. So let's compute for the value of R. Again, the final resistance is RO, 1 plus alpha delta T. So this is the equation. So let's just substitute the given. We have 4.45 ohms. This is RO, 1 plus alpha. So alpha is the temperature coefficient, 4.3 times 10 to the negative 3 per Celsius degree. And then that is to be multiplied by the change in temperature. So change in temperature is simply 60 minus 0. So we have 60 Celsius degree. Okay, so this is equal to 5.5981, or this is 5.60 ohms. So as you can see, if there is increase in the temperature from 0 to 60, there will be also increase in the resistance, 0.45 ohms to 5.60 ohms. So we are now in electric power, and power can be computed in this manner. Okay, so we have this one. Okay, so change in Q over change in time, that is our computed current. Okay, di ba kanina, we have current is equal to change in Q over change in time. And then, of course, V here is the potential difference. So to compute for power, power is simply equal to I multiplied by V. Again, power is expressed in watt, and then I is in ampere, and of course, the potential difference or voltage is in volts. Okay, so that's the first equation for the power, and then power can be also computed using Ohm's law. We will be deriving the one quantity from Ohm's law. For example, we will be deriving the formula for V, for I, or for R, and then we just need to substitute that in this equation for us to arrive on a different equation for power. So that is equal to this one and V squared over R. So for us to compute for power, depending on the given, if the given is potential difference and current, we just need to use this one. If the given on the problem is current and resistance, we can use I squared R. And then if the given are potential difference or voltage and the resistance, we can use this equation. So this is, or these are the equations for electric power. In the problem, we have the given current, 0.40 ampere. So this is the current, a voltage of 3 volts. So this is V. We are asked to get the power delivered to the bulb. So power is simply I multiplied V by V. So V times I, V times I. So this is I, this is V. This is equal to 1.2 watts. And then energy is already derived in our previous slides. And energy is equal to power multiplied by time. So again, power is energy divided by time, or that is work divided by time. So to compute for energy again, so that's power multiplied by time. Power is 1.2 watts, so that's the computed power multiplied by the given time. So given time is 5.5 minutes, and you need to convert 5.5 minutes to seconds. So 5.5 minutes or 5.5 minutes multiplied by, in every 1 minute there's 60 seconds, so 5.5 times 60, we have 330 seconds. So that's equal to 4 times 10 squared joules. So the unit for energy is joule. So in this problem, current is given. I is equal to 3 amperes. And then we have resistance. Resistance is 3 ohms. We are asked to get the energy in 45 seconds. So energy, the given time is 45 seconds. We're looking for the energy. Again, energy is equal to power multiplied by time. And power, based on the given, we have I and R. We can use this formula, I squared R multiplied by time. So this is I is 3 ampere, 3 amperes squared, and then multiplied by 3 ohms, and then multiplied by the time given, 45 seconds. So this is 9 times 3, 27. 27 times 45. This is 1,215 joules. Okay, so this is the energy, 1,215 joules. Now, let's proceed with wiring. So, again, resistors can be connected in different ways. It can be connected in series like this. Okay, they are connected in series. Or they can be connected in parallel. Okay, so this one is in parallel. Okay, in series connection, so we have different properties. Okay, so what is the value of the voltage or potential drop or potential difference and the total resistance and current when it comes to series and in parallel? Okay, in series, to get the total resistance, so we have resistance 1 and resistance 2. So to solve for the total resistance, so total resistance is the equivalent resistance. That is simply the sum of all the given resistances. So if there's additional resistance here, for example, this is R3, you just need to add R3 here. Again, total resistance is equal to R1 plus R2 plus R3, or that is simply the sum of all the resistances. So this is the total resistance, and then the current here, this one, the current flowing in the circuit is constant. So meaning the current here, I1 and I2, they are the same. So I total is equal to I1 equal to I2, and then if there's another resistance here, that's equal to I3. And then how about the voltage? This voltage. So the voltage here is simply the sum of the voltage on R1 and then the voltage on R2. So meaning the total voltage is simply V1 plus V2, and then again if there's the presence of resistance 3, that's equal to V3, and so on. So this is the properties for the series connection. For parallel connection, so to get the total resistance, that's the reciprocal of R total, 1 over R2 plus 1 over R3 plus additional resistance. And then for the current, so current here is not constant, so that's equal to I1 plus I2 plus I3 and so on. And the voltage here, so whatever be the value of the voltage here, that is the same voltage within or in the whole circuit. So meaning total voltage is constant, so that's equal to V1 equal to V2 equal to V3 and so on. So this problem is about connection of resistors in series. Okay, resistors in series circuit. Okay, again, in series circuit, we need to remember the properties. For example, for the total resistance, because in this problem, we are asked to get the total resistance. But the first question here is find the current. So we cannot solve the current without solving first the resistance. So we need this is the formula for resistance. So the total resistance in the circuit is equal to the total voltage divided by the total resistance. So the total voltage is given, so that is 12.0 volts. But the resistance, the total resistance is not given. So since this is in series, the formula for series connection, so R total is equal to R1 plus R2. So R1 is 6 ohms, R2 is 3 ohms, so 6 plus 3, so that's equal to 9 ohms. So 12 volts as the total total potential difference or total voltage divided by the total resistance. So the current is 1.33 ampere. Again, so this is series connection. So we conclude that whatever be the total current, that is equal to the current flowing in the entering in the 6 ohms, and also that is also the value of the current in the 3 ohms. So we can compute per power, because the second question here is what is the power dissipated in each resistor. So we need to compute the power on 6 ohms and the power on the 3 ohms. So in 6 ohms, Again, power is equal to I squared R. Okay, we will be using this formula, but you can use other formula like B multiplied by R or B squared over R. But since the given here is our current and also resistance, we can directly use this formula. Current is computed. Okay, that is constant. We have 1.33. Resistance is 6 ohms. So this is 6 ohms. So the answer is 10.6 watts. And then for the second resistance, 3 ohms. Still, we have constant value of current. That is equal to 5.31 watts. Letter C, the total power delivered. So we just need to add the power dissipated in resistance 6 ohms and in resistor 3.00 ohms. Okay, so 10.6 watts plus 5.31 watts. So that's equal to 15.91 watts or 15.9 watts. 3 resistors, 411 or 110, 40, 110, and 150, they are connected in series in a circuit. Again, they are connected in series. So we can say that this is R1, R2, and R3. Okay, they are in series. And then so this is 40 ohms, 110 ohms, and 150 ohms. We are asked to get the total resistance, and total resistance R total. Again, this is series connection, so therefore the formula is R1 plus R2 plus R3. Just get the sum, 40 ohms plus 110 ohms plus 150. This is equal to 300 ohms. The total resistance in this circuit is equal to 300 ohms. So in this one, so the resistors are connected in parallel. Meaning if this is resistor 1 connected in parallel the resistor 2 and also the resistor 3. Okay, so we have R1, R2, R3, and then the formula for R total is 1 over R1 plus 1 over R2 plus 1 over R3. Meaning that is equal to 1 over 3 ohms, 1 over 6 ohms, plus 1 over 12 ohms. This is equal to so that's 1 divided by 3 over 3 plus 1 over 6 plus 1 over 12. So the answer here is 7 over 12. So 1 over R total is equal to 7 over 12. We're looking for R total, so therefore we need to get the reciprocal. This is equal to 1 point. Okay, I will repeat my computation. 1 divided by 3 or 1 over 3, 1 over 6, 1 over 12. Okay, this is 1.71. So 1.71 ohms. So here's the total resistance. 315 ohms. 315 ohms. And 225 ohms. Are light bulbs. So they are light bulbs. They are connected in series with a 24 volts battery. Okay, they are connected in series, and then the value of the voltage is 24 volts. So we need to get the current that passes through each bulb. So if we're going to draw that, we have they are connected in series, and then we have 5 bulbs. We can say that this is the first bulb, second, third, fourth, and fifth. And then they are connected in series with the 24 volts battery. So they have the same value. So this is 15 ohms. This is also 15. This is 15. This is 25 ohms. This is also 25 ohms. So the question here is, what is the current? So for us to compute for current, we need to solve first for the total resistance. And total resistance is simply the sum of all resistances. So meaning 3 times 15 is 45 ohms. 2 times 25 ohms is 50. So therefore, total resistance is 45 plus 50. This is equal to 95 ohms. And again, total voltage is 24 volts. So we can compute for current. Current is V over I or V over R. So this V total over R total. 24 volts divided by 95. So 24 divided by 95. So this is equal to 0.25. Okay, 0.25 ampere. Flowing there is 2.25. And that 2.25 is the value of the current we use for, or we computed for letter B. Meaning, our value of currents for the first resistance or the remote speaker and the main speaker, the total of that is equal to 2.25. Power can be solved using VI. So the formula used here is current multiplied by voltage. So current is 0.750 for the first resistance or for the first speaker. And then we have constant value of the voltage. The same thing with the second resistance. That is, the current is 1.50. And then voltage is 6 volts. So we have 4.50 watts and 9 watts. In which we have this formula. So this is the value of the electromotive force. So the value of the electromotive force is the voltage in a battery. So minus I multiplied by small r. So this is the current flowing in the battery or in generator multiplied by the internal resistance in the battery or in a generator. So just subtract that from the value of the electromotive force, so we can compute now for the voltage. So in this problem, we are asked to get the terminal voltage. Okay, again, for terminal voltage, the formula is equal to E minus I multiplied by R. But in this equation or in this problem, what the PowerPoint did is he computed first for IR. So IR, so this is the IR, and then after that, he subtract the IR from the value of the electromotive force. In this problem, the value of electromotive force is 12 volts. Internal resistance is 0.01 ohm. So we can compute for the V or the IR. So that's equal to 10 multiplied by 0.01. The value of the voltage is 0.10 volts. Okay, and then subtract that from the value of the electromotive force. So that's simply 12 volts minus 0.1. So we have 11.9 volts as the terminal voltage. So here is for letter B, there's the change in the value of the current. So the current now is equal to 100 amperes. The value of the internal resistance is the same. So the same process. He computed first for the voltage, then after that he subtract that from the electromotive force to compute for the terminal voltage. So the terminal voltage is equal to 11.0 volts. So the last topic is about Kirchhoff's rule, and then under the Kirchhoff's rule we have two rules. The first rule is junction rule, then the second is the loop rule. So what's the difference between the two? Of course, junction rule refers to the junction in the circuit, and then loop rule is the loop in the circuit. So according to the junction rule, the sum of the magnitudes of the current directed into a junction is equal to the sum of the magnitudes of the current directed out of a junction. So meaning if this is directed out, this is also directed out, this is directed into the junction. So the formula is simply this current plus this current equal to the current directed into. So that is the equation. So if I'm going to solve for that one, so that's equal to 5 ampere plus 2 ampere, and that is equal to it should be equal to 1 ampere. So that should be the case. Again, all the current directed into is equal to the current directed out of a junction. For the loop rule, around any closed circuit, the sum of the potential drops equal the sum of the potential rises. So we need to get the total potential drop here, or the total potential difference, and then the answer should be equal to 0. So we need also to consider, or to be reminded of the sign conventions. So here, for example, here is the direction of travel. Okay, so the direction of travel can be set by you or by anyone. So it depends on the one who analyzed this circuit. So according to the sign conventions, if the travel is here, okay, for the IR first, okay, sign conventions for the resistors. If the travel is opposite to the direction of the travel of the current, if they are opposite, we're going to use positive IR. And then if they have the same direction, on the same direction, so this is the direction, and then this is the direction of the current, so we're going to use negative IR. So in our case here, the direction of current is this one, this direction, and then the set direction of travel is also here. So they have the same direction, meaning the value of IR is negative. So in that case, so for us to get the IR here, so that's simply 5 ohms multiplied by 2 ampere, and then that is negative because they have the same direction. Okay, on the other side, okay, of course that will be the sign conventions for the electromotive force. So for electromotive force, we need also consider the direction of travel. Okay, for the direction of travel, so according to that, if the direction of travel from negative to positive, so that is from negative to positive, the direction or the sign will be positive. Okay, in this case, the direction of travel is here, and then according to the direction of travel, negative first before the positive. So negative terminal to positive terminal, we're going to use positive electromotive force. So in this case, if this is the direction of travel, so here is our electromotive force, and then according to that, according to the diagram, negative to positive. So negative to positive, meaning we're going to use positive electromotive force. But if this is positive to negative, we will be using the negative electromotive force. Okay, so this is the travel, and then positive to negative, we're going to use negative value of electromotive force. The same thing with this. Okay, so this is the last topic. Okay, this is about Kirchhoff's rule. We're going again to apply the loop rule and junction rule. As you can see, we have here junction B, and then we have here two loops. Okay, this is loop C D E B. So this is the first loop. Okay, and then we have here another loop. So the question here is, what is the value of IH, or the current? As you can see, the current IH or IH is directed out or leaving. So that is leaving, leaving from the junction, directed out of the junction, and then IA is directed in the junction. The same thing with IB. So IB and IA, they are directed towards or directed in the junction B. So we can use the junction rule here. So at junction B, we can compute the total current. So total current is equal to the sum of the current directed in IA plus IB equal to the current directed out IH. So this is the first equation. Now after that, so using the junction B rule or the junction rule, still we cannot solve the value of the currents, the IA, IB, and IH. So meaning we need to proceed with the loop rule. Okay, for the loop rule, we can set two loops here. The first loop is CDEB. Okay, that is CD. Okay, so CDEB. So here is the first loop. So CDEB. Okay, and let's say the direction is here. Okay, the direction is clockwise direction. Okay, in that case, so let's solve for the total potential difference. Let's get the potential drop and the potential rise. I will be starting here. Okay, again, for the loop rule, we'll be just using the formula IR. Okay, and then for electromotive force, we just need to identify if that is a positive or negative electromotive force depending on the terminal. So in that case, okay, so here is the direction of current. And then as you can see, they have the same direction with the travel. So if they have the same direction, so the value is negative. So this is negative IH multiplied by the value of the resistance, 1.2 ohms. So that is for this component. And then so there's no component at D to E. Okay, there's no component here. Then let's proceed here. So this is 12 volts. Again, here is the direction of the travel. And then according to the direction of travel, this is negative first before positive. So negative to positive, we use positive electromotive force. So positive 12.0 volts. Okay, then after that, let's proceed with this one. Okay, the current here is IB. The current here is IB. And then the IB, the direction of the current is the same direction with the travel. So meaning we will be using also negative. So this is negative IB multiplied by 0.0 ohms. And then again, this should be equal to 0. Okay, so in this case, we can simplify this equation. So meaning this can be simplified as IH multiplied by 1.20 ohms plus IB 0.01 ohms, and that is equal to 12.0 volts. Okay, so this is the second equation. Actually, this is our first equation. Now this is our second equation. But as you can see, we still cannot solve the value of IA because there's still a missing equation. So we cannot solve the equation, the currents IA, IB, and IH using equation 1 and equation 2. So we need to proceed to the third equation. So the third equation is the equation for the second loop. Okay, for the second loop, we'll be considering the lower loop. Okay, for the lower loop, so that is the loop BEFA. BEFA. So here's the loop BEFA. Now let's focus on the lower loop. And then let's set a direction. Okay, let's say the direction is the same. Okay, we are referring to this loop. And then let's say the direction is also counter, or this is clockwise. This is also clockwise. Okay, I will be starting here at B to E. Okay, at B to E here. Okay, so I'll start with this. Okay, as you can see, IB is opposite with the direction of the travel. So they have opposite directions, so meaning the sign is positive. So this is positive IB multiplied by 0.01 ohms. So that's the resistance here. Okay, that's positive. And then the second one is, this is the direction of travel again. And then, kung napansin natin, this is positive to negative. So meaning the sign is negative. Negative 12 volts. And then let's proceed with the second component. So the second component is 12 volts. So in 12 volts, again, here's the direction of travel. So that will be negative to positive. So negative to positive, we're going to use positive electromotive force. So that's positive 14 volts. Then the last is IR. Okay, here's the direction of travel of the current. Then here's also the direction of the travel. So it's the direction of current. So they have the same direction. So meaning this is minus IA multiplied by zero point 0.1 ohms. This is equal to 0. Okay, what we just need to do is to again to simplify this. Okay, so this can be written as for this equation, this can be written as IV multiplied by 0.01 ohms. Okay, again, then just add the two. So this is plus 2 volts, and this is equal to 1 ampere multiplied by 0.1 ohms. So that will be the simplified equation. So we have, this is the second equation, and then this is our third equation. Okay, so let's based on the first equation, the second equation, and the third equation, so let's compute for the current. Okay, so actually that will be for the first equation. Again, we have this equation, IA plus IB equal to IH. Okay, this is the first equation. And then for the second equation, we have IH multiplied by 1.20 ohms. Okay, plus 0.01 IB equal to 12 volts. So this is the equation 2. And then for the last equation, we have this. Okay, so that is IB multiplied by 0.01 ohms. Okay, plus 2 volts equal to, okay, that's equal to IA, and then multiplied by 0.1. Okay, so here are our equations. So what we need to do is we're going to use the algebra. Okay, so we have here three unknown, IH, IB, and IA. So therefore we need to use three equations for us to get the three unknowns. Okay, just use the basic equation for algebra. Okay, what you need to do is, so since you have this given, okay, the IH can be replaced by IA and IB. So that means the IH here can be written as IA plus IB. Okay, substitution method. Then 1.20 ohms plus 0.010 IB equal to 12 volts. Okay, so in this case, I'll be writing this one into, okay, or you can put the 12 volts inside here, so that will become negative. Okay, this can be negative, and that will be equal to 0. Okay, so in the second equation, so therefore this can be simplified as IA and multiplied by 1.20 ohms plus IB and then 1.20 ohms. Okay, plus 0.010 IB minus 12 equal to 0. Okay, you just need to simplify. You can add IB, the two IBs. Okay, you can add the two. And then for the second equation, so this is the second equation. So that can be written as, this is negative. So this is negative or equal. So therefore that can be also written as negative IA. Okay, this one. So this is negative IA. And then multiplied by 0.1 ohms. Okay, then plus IB 0.01 ohms, and then that is plus 2 volts equal to 0. Okay, so you have here two equations. Then as you can see, guys, you have here IA and you have IB. You have two variables. So two variables, two equations, you can compute for the two variables. Okay, just use algebra here, and then the final answer should be IH is equal to 10.08 ampere, and then IA should be equal to 19.10 ampere, and then for IB, this is negative 9.02 ampere. Okay, the negative value here means that the assumed direction of current IB is not correct. So instead of the setting the direction of IB directed out of the junction, it should be directed in, or vice versa. Okay, so that's the meaning of the negative value. And then how to get the IH here? So you need to solve first for IA. Okay, so using these two equations, we can compute the value of IA or IB. Okay, if you want to solve first for IA, after solving for IA, you just need to substitute the IA here, the value of IA here. So therefore, you can compute for the IB. Actually, you can use this equation or the second equation. So after solving for IA, next step is solve for IB because you already have the value for IA. Okay, and then after that, so you already have the IA and IB, you can use this formula to solve for IH. So that's the value. Okay, so this is the content of chapter 9, electric circuits. So thanks everyone for watching. Bye bye.